Okay, I think the recording has started. So, am I audible? Is there any interference? Are we clear to go? You can hear my voice properly, right?
Yes.
Okay, so it's 6:10 already. I think it's time to begin. So, before going into week two, do you have any doubts or any queries or any issues with the week one content so far? If you would like me to revise something that we have discussed last week, I can do that. Otherwise, I can move to week two content. So let me know if you have any issues. Just a sec. Okay, so we start off from where we ended last week. So if you're joining for the first time, my name is Manav. I'm one of the teaching assistant for this course. I'm a PhD student at IISER Bhopal in my year three, and I am my research area is mostly in the field of reinforcement learning and multi-agent robotics. So if you have any queries or any research related doubts or issues, you can feel free to contact me. So last week where we stopped was something called as stochastic averaging. Okay. So we had defined what we mean by a Q function. So my Qt of A is nothing but my R1 plus R2 plus dot R of T and the number of times I have selected uh, arm A. Okay. So this is my value function. What we use the value function for? We use the value function so that we evaluate the strength or weakness of a policy. So each particular action, so this is an immediate RL problem. We don't have any idea or any notion of a state space here. All we are dealing with is the action space, wherein if we pull a lever, we get a reward, we get an immediate reward. So this is the multi-arm bandit problem we are looking at. So for that, my Q value is basically the sum of all the rewards divided by the number of times that arm A has been pulled. So if I write it more compactly, so my Qt of A can be written as Qt of minus 1 A times NA plus RT, and AT is equal to A upon NA plus 1 AT is equal to A. So what it tells me is all I'm doing is whatever was the Q value that I had at time t minus 1, I'm multiplying it with the number of times that particular arm has been pulled. So that gives me basically R1, R2, till R of t minus 1. Then I add in R of t if arm A has been pulled at RT, and then I divide it by NA plus 1. Okay, so I'm just doing an incremental addition. So the difference in this two formulation or the strength of the second formulation is that I no longer need to keep a history of all the rewards that I have accumulated so far. So let's say my capital T is 1000. Okay. So I don't need to keep a list of the reward I got at time 1, time 2, time 3, up till time 1000. All I need to care about is the total number of arms that I have pulled so far, which is N of A. I need to worry about that. And my last estimate of the Q value, which is Qt minus 1. If I knew these two, I get the immediate reward that I have. I add it on the fly. Okay, so this is an on the fly averaging that I'm doing. So if I were to represent it even more Exactly. So let's say my AT is A. So this whole term becomes 1. Okay, so you have Q of T minus 1 A N A divided by NA plus 1 plus RT upon NA plus 1. Okay, I can write it this way, and this can further be written as UT minus 1. So 1 minus 1 upon NA plus 1 plus RT NA plus 1. Okay. Now, if I just pull the terms here and there and do even more simplification, what I end up is I get that my QT of A is nothing but Q T minus 1 A plus 1 upon NA plus 1 times RT minus QT minus 1 A. Okay. So this is something very important. You should probably make a note of this. Maybe I can highlight it. Uh, so make a note of this equation. This will be helpful later on when we are looking at this Q function based RL, even when we move to the RL problem from the immediate RL problem. Slides, yes, they will be shared with you. Uh, Actually, I have submitted the slides to the NPTEL repository. So usually what happens is wherever you see the course outline, there you have the like where you have week 1, week 2, week 3. Below week 12, there is usually a problem solving session, and there usually you get all the videos and all the slides. So I don't think NPTEL team has updated that yet, but I think so they will do that soon. But from my end, I have submitted it. Or maybe what I can do is I can post the drive link, okay, of where I'm maintaining the slides. So just a sec. Okay, so this is my drive link where I'm uploading all the slides. And if you want the videos of the previous, if you want videos of the previous class, so this is my YouTube channel. This is where I am uploading all the lectures. So you can go to these two links and get all the slides and the recordings. Okay. So week 2 slides won't be there because I'm currently making it. So later on, you can figure it out. But you can definitely find week 1 ka slide over there. Okay. So the way you remember this formula is, so you have Qt of A, the Q value at time t is dependent upon my Q value at time t minus 1. And on top of that, what I'm doing is I'm adding this extra term. So another way to look at this is you say that this is new estimate. Okay. My new estimate is nothing but my old estimate plus the step size times my target minus old estimate. Okay. So you can remember it this way. So now if you look at this from in this way, let me also highlight this part. Uh, Maybe I use pink and okay. So if you look at the equation over here, so what it says is that my new estimate is nothing but my old estimate plus some step size parameter and my target minus the old estimate. So you can think of the term inside the bracket as some sort of an error function. Okay. Now, as soon as you look at this equation from a broader lens, you will say that, okay, this equation is similar to what we do in machine learning, which is my gradient descent. But in that case, what happens is my the gradient I compute, I always go in the negative direction. But since this is an RL problem, we are trying to maximize the reward. I am trying to take a step in the direction of the positive gradient. Okay. So you have the old estimate plus the step size. Is this same as incremental means method used in Monte Carlo method? Yes, you can think of it like that. It's similar to that method. Yes, it's exactly the same, I would say. It's an incremental means method by which you keep on approximating the average. Okay. So the reason why we call it as stochastic averaging is that because if you look carefully at this error term over here, so here this RT is basically something that is a target that we are chasing. Okay. But is it really RT that we are chasing? No, right? What we are actually looking for is basically the expectation of RT. And what is my expectation of RT? Anyone? It's nothing but my Q star, right? Q star A star. So this is actually my true value. But instead of expectation of RT, what I'm doing is I'm drawing a sample from the reward distribution. And based on that, I'm making an update. Okay, so there is a bit of stochasticity that is involved in this case. So that's why we call this method as stochastic averaging. Okay, and note that this equation 1 only holds true for what do you think would be the condition where equation 1 holds true? The basic assumption is that it's a static distribution, right? I mean, equation 1 holds true regardless. Okay, this equation over here, the one that I have highlighted in pink color, this equation holds true everywhere. Okay, the only difference that we have when we move from a static distribution to a dynamic distribution, okay, or a time dependent distribution, the only difference that we make is in the step size. Okay, so this term over here is something that changes. Now, if you notice, in a static distribution, my step size is actually dependent on the number of steps that I've taken. So here, as the number of steps increases, as my NA goes to 1,000, 10,000, 1,000,000, or some other number like that, my actual update that I'm doing on the error term, as in the value of each update of the error term keeps on decreasing with incremental update that we keep on doing. And you can think of it intuitively as well, because if like you're taking an average of a very large quantity, like let's say there are 10,000 points, so the weight of each element in that average becomes very, very small. Okay, so if you just work around, you can directly go from this here to here. Okay, so these two are equivalent. So this is something that makes sense also. Now, but what happens in a dynamic distribution is, in dynamic distribution at every time step, so in let's assume uh, in my static distribution there is a, I'm considering a Gaussian curve which is parameterized by a mu and a sigma. Okay, for this is for a static distribution. Similarly, if I want to move to a dynamic distribution, my Gaussian gets parameterized on my mu t and sigma t. So you see my mean and my variance are now time dependent. So my mu and sigma evolves with time. So based on that, the distribution curves keeps on shifting its shape. Okay. Now what happens in that case is, when we talk about let's say dynamic distribution. So because this keeps changing, I want my Q value update to take in or incorporate the more recent changes that I have made so far in comparison to some 1,000 time steps ago, right? So for that, this step size parameter where we do 1 by NA, okay, this won't help, because with increase in the number of samples that I'm drawing, with increase in the number of arm pull that I'm doing, the dependent my step size, I mean the updation part, the effect of the updation keeps on reducing. So in this case, for a static distribution, usually what we do is we work with uh, a constant step size parameter. So in this case, my step size parameter. Uh, so in this case, my step size parameter is denoted by some variable alpha. Okay, for a static distribution, and my alpha always should lie between 0 and 1. Okay. So the reason we do that is my alpha is necessarily less than 1 and is greater than 0. The reason we do that is because, let's say I pull the arm one time, that arm pull will get a weightage of alpha. Now if I pull that arm second time, the second arm pull will get a weight of alpha, but the first arm pull will now get a weight of alpha square. Okay. And so on. So the weight keeps on, I mean, the weighted average keeps on decreasing exponentially as the arm moves towards the past. Okay, so the most recent arm pull gets a weight of alpha. Second recent arm pull gets a weight of alpha square, alpha cube, and so on. Okay, and since alpha is between 0 and 1, it's actually a decaying quantity. It will eventually converge. Okay, so this is all about stochastic averaging. Now, in week 2, we look at a new class of problem. Okay, so this not exactly a new class of problem or a new method or a new approach to solve the bandit problem, to solve the multi-arm bandit problem. So we'll be looking at something known as UCB1, or what we call as the upper confidence bound algorithm. Okay, I like this. Okay. Now this algorithm holds true for a MA bandit problem. Okay. I hope we are clear with what is a bandit problem. So in a bandit problem, you have some slot machines, and each slot machine has some associated lever, and you pull the lever and you get a certain reward. Okay, so there's a question. So in case you mention the target is U, what do you mean by that? Target is U. Can you rephrase your question? I couldn't get it. Or do you want to unmute? No? Harpreet, you might want to unmute and ask so that I can understand what you're saying. Okay.
Sorry, can you hear me?
Yeah, sure.
So, just a question. You said there's a stationary distribution, right?
Mm-hmm.
In the stochastic averaging, we're looking to have a target.
Yeah.
Is this the is are we looking to try and figure out the in the state the value of mu by that whole process of stochastic averaging?
Yes.
Is that what we're
Yes.
looking to do?
Yes. So what I'm actually looking at is to find out the value of Q star A star. My Q star A star is basically the true value of the optimal arm. Okay. Small q always denotes the true value. So let's
Correct.
say I'm looking at I look at this casino thing. So the casino owner might have set some reward behind each machine. Okay. So let's say machine one has some reward curve, machine two has some other reward curve, and
Yes.
some other reward curve, and so on. Okay. So this
Yes.
true mean is something that the owner has already set. We are trying to estimate that.
Okay, and that is by sampling because we don't know exactly what.
Correct, correct. So the way we do that is we pull the arm n number of times. We collect all the rewards that we have, R1, R2, R3, and we take an average over that. Okay. What we are doing here on the first line, I have written. See that?
Correct.
The first line.
Correct.
But the issue is, let's say my n keeps on increasing. I need to maintain a history of all the rewards that I've accumulated so far,
Yes.
right?
Yes.
So it's R1, R2. I maintain it in a list and then keep averages at the end. But I don't
Yes.
want to do that. Okay. I don't want to keep a list of all the rewards that I have. Instead, what I want to do is I just want to know the last Q value that I have updated. And based on that, I take the current R and make a new update.
Okay. So
Okay.
every time you update the R.
Yeah.
So why so it is deterministic, right? It is not it is a stochastic process in the sense at the end of it you will get a number which is correct, correct?
Approximately. Asymptotically, we'll get something which is correct.
Asymptotically you will get something. Okay. Thank you so much.
Now you look at it. If you look at it, the error term over here. So it's RT minus QT minus 1, right? So what actually is my true goal? All I'm trying to do is I want to estimate the expected value of the reward, which is my Q star A star. But instead
Yes.
of having expected a value of reward, I'm instead taking a sample of the reward. So that's why I
Okay.
call it a stochastic averaging.
Okay. Okay. Thank you, sir.
Okay, sure.
And this is done for each of the arms, right?
Yeah, yeah. If that particular arm is not pulled at that time step, okay. So let's say, yeah, if that arm is not pulled, then this quantity over here, second line,
Mhm.
this becomes 0.
Yes.
So there is no update. My Qt is equal to Qt minus 1.
Okay. Okay.
Okay,
Thank you. Thank you, sir.
sure. Okay, so last week we had seen some optimalities associated with the multi-arm bandit problem. Okay, so those optimalities were asymptotic correctness. What we mean by asymptotic correctness is that given k arms, given k bandits, if I sample each arm sufficiently enough, asymptotically I'll reach to the correct solution. Second is known as the regret optimality. What regret optimality tells me is that assuming I know the optimal arm from the start and the process of figuring out the optimal arm. Okay. So if I know the optimal arm from the beginning, and the other ways we do the arm pulling using the epsilon greedy strategy or any other strategy. So the time that is wasted in figuring out the optimal arm is known as the area of regret. So I'm trying to optimize so as to minimize the time taken to reach the correct solution or minimize the regret. So if I plot it, so if this dotted line is my Q star A star, okay, this is the true solution. And with time, I do some number of arm pulling and I eventually reach that point. Okay. So the area that lies in between this this part is my regret area. Okay. So my goal is to minimize this regret or not. It can't go exactly to 0 because eventually you have to do some kind of exploration. But we want to maybe put an upper bound on the maximum possible regret that each different algorithm can give us. So we have discussed so far two exploration strategies. First was the epsilon greedy strategy, and second was the softmax strategy. What epsilon greedy strategy does is it selects the optimal arm with probability 1 minus epsilon, and with probability epsilon, it selects the non-optimal arm. It selects some random arm. Okay. And softmax function basically weighs in the relative strength of the Q value with respect to the other arms, and based on that, it makes a probabilistic, not probabilistic. I would say, yeah, it selects the arm which has the highest weighted average over the other Q values. Okay, and last optimality is known as stack optimality. So this basically tells me that given two values epsilon delta what is the probability that the arm that I sample, my Q star of A, lies within epsilon bound of Q star A star, and I classified correctly with probability 1 minus delta. Okay, so this is the back optimality. So now for upper confidence bound algorithms, or UCB1, so there are k arms. We start with k arms. Okay, and the way it works is, so you start off with a stationary distribution. So this Q star of A is basically expectation of that stationary distribution. Okay, the way you do it is you pull each arm once in the beginning. Okay, so when you start, so if there are k arms, you pull each arm one time, and then after that, what you're doing is you play arm J that maximizes what Qj plus some 2 ln n over nj. Okay, so all I'm looking for is argmax of J belonging to the action space that maximizes this quantity. Okay. Now, can someone tell me what could possibly be the strength of this approach in comparison to the epsilon greedy strategy that we discussed last week?
In epsilon greedy, we do the exploration by choosing a random arm, but
Correct.
that random arm could be the one that has a very low.
Correct. That's true. So the exploration is something that we do in a uniform fashion. Okay. So whenever with probability epsilon, we sample an arm very randomly. So that there is a component of randomness in that case. But in UCB algorithm, this is a deterministic algorithm. Okay, so what you do is you're trying to maximize the arm that has the highest Q value, but in doing so, what you're doing is you're also looking at this small term over here. This is known as the confidence bound. Okay, so how confident you are in selecting arm J, and this is given by this quantity. So there is also an additional term C here. So this C is basically controlling the it controls the scaling of the confidence bound. It means C is also known as the exploration rate. So if C is very high, that means the confidence bound keeps on increasing. So based on the application that people target, you can set uh, appropriate confidence bound and get the problem solved. Okay. So okay. Now if I represent what we discussed pictorially, so we have, let's say, arm Q1. Okay, so this is over here. Let's say this is arm Q2. This is arm Q3. So Q3 is here, Q2 is here, and arm Q4, let's say, is here. Okay. Now, what this tells me is that, let's say, this is the confidence bound of arm Q1. This is the confidence bound of arm Q2. This is for Q3, and maybe this is for Q4. So in this case, which arm I'm more likely to select in the next iteration? What do you think?
Q3.
Q3. Why?
Sorry, Q1. My mistake. Q1.
Okay. Why Q1? Why not Q4? Q4 has higher intrinsic value, right? If you look
Yeah,
at
but
the
if you, so I think the math says that um, uh, if you have a Q1 and the confidence level,
Mhm.
um, that term actually is greater than Q4 and the confidence level. I think that's what it
Correct.
meant.
So initially what you're doing is, if you look at this, okay, this vanished. Okay, so if you look at this term, if you look at this confidence term, so you see it depends
Yeah.
on two parameters. One is ln of n. What is ln of n? N is basically the number of arm pull you have done overall. Okay, so far, how many times you have pulled each arm, and nj is how many times you have pulled arm j. So if I have pulled 100 arms so far, out of 100, how many times I've pulled arm j? Okay, so initially there is a 1 by n dependence, okay, for each arm pulling that we do. So let's say one arm, let's say arm j isn't pulled for a long time, okay. So because of that, the confidence bounds increase by ln of n. That means my nj is constant for a long time. It's fixed for a long time, but my small n is increasing. So that means for each time instance that I have not sampled that particular arm with time with log n time, my confidence bound slowly increases. But as soon as I sample it, the confidence drops over 1 by n. Okay. So you see, in the long run, the more number of samples I do, it keeps on reducing the confidence that I have. Okay. So initially, whichever region has a higher uncertainty, I'm more biased, or I'm more keen to explore that particular arm over there. So that's why even though arm Q4 has the higher uh, estimate Q value than arm 1, but because the confidence interval of arm 1 is bigger, I'm more likely to select arm 1. Now let's say what happens is I selected arm 1, and based on that I update my confidence interval. So now my confidence interval looks like this. So this is my new mean, and this is where my confidence interval is right now. Okay. So now I know that arm 1 is bad, but one step before I couldn't have said this with more confidence. Okay. So that's why with more number of sampling or more number of time steps, we are able to put an upper bound on the level of confidence on which we can assert that this arm is correct, and I'm gonna exploit that, or I'm going to explore that. Okay. So you see, exploration and exploitation is inherent in the equation that I had highlighted in the previous time steps. Okay.
So the question is
Mhm.
it mandatory to do this? Because you did not. So if there is a Q3 there, which also
Mhm.
seems to be having a lot of confidence level, which looks like it has not been selected for a very long time. Why didn't we choose that? In the sense, why didn't we try and select that
Because
particular
its
arm?
Q3 value is less, no. So even if with Q3, including the confidence, I won't get a value which is higher than Q4. So you see the lower bound of Q4 and the upper bound
Mm,
of Q3. So there is a
mm,
gap. Okay. There's a small gap.
okay.
I mean, the best of Q3 is worse than the worst of Q4. So I won't select Q4. I
So
will only select if
there's a possibility that we don't select Q3 for a very long time if this is how it is.
Okay, so if you don't select Q3 for a very long time, it will slowly start increasing its length. Then maybe you are you might
Oh,
end
it.
up selecting.
Oh, okay. You're saying even though you don't select it, its confidence will start to increase because of the login factor.
Correct, correct. The
Hmm.
increase is
So
log n. The
basically, all these arms come into play every time.
not every time. It's like
When do we reach some kind of a conclusion that okay, this is it. I will only keep using a specific arm.
okay. So if you look at log n, so log n saturates after if I take n to be some large number, log n
Hmm.
more or less saturates. So the increase won't be that much. Okay,
Okay.
but 1 by n has a steep decrease. Okay, so let's say I have sampled each arm, say 10 times each. Okay, so now I have like let's say a 95, 96% confidence that okay, this is the arm. I'm gonna keep exploiting that. So you see that increase saturates after certain
Yes.
time period because of the
Yes.
log factor.
So this is another way to find out if you have a normal distribution. This is another way to find out the mu, right?
Correct. Correct.
So which of this is
So
better? The one that we just the stochastic average one or something like this? What is the use case of using either of them?
no, here also you're doing stochastic averaging only. Stochastic averaging is just a way in which we aggregate the Q values. So let's say
Okay,
I
this
have
is
put
just a graphical representation of that. Is it?
No, yeah. So this is an algorithm. That's a way of
Hmm.
aggregating the information. So let's say I'm
Okay.
doing arm of QJ. How do I update the QJ? I
Hmm.
need to take QJ minus at QJ at time t minus one, then take the reward,
Correct.
update it. So that's an
Correct.
updation method for my Q value. That's not an
Yes.
algorithm.
Yes.
Okay, so this is the algorithm. The other algorithm was something known as epsilon greedy, which we discussed last week, wherein
Yes.
with epsilon probability, I select some random action, but with 1 minus epsilon, I select the argmax of Qj.
Okay.
So the only issue with that was if I want to explore, that exploration was completely random.
Yes.
Here it's more or less deterministic. Okay.
Hmm. Hmm.
So it's like I am bound to explore each arm
Hmm.
some number of time before I arrive at some conclusion.
Hmm.
So it's
Hmm.
inherent in this equation. Okay.
And if I can ask, all
Yeah.
these, if you go to the slide that you have, and sorry, the next one, these
Yeah.
Qs, these are what? These are rewards, right? Are these rewards
So my Q star of A is the true value. Okay.
of
Which you
of?
of each arm. So my arm A for arm A, my Q star of A is the true value. It's true value of arm A. So this is something that we don't have access to. Okay. This is something that
Hmm.
the environment gives. Environment knows. The agent doesn't have an idea. The agent tries
Yes.
to estimate this Q star value. So
Yes.
my capital Q is an estimate
Yes.
of the reward of arm A.
Yes. Yes.
So my goal is to make my capital Q as close as
Closer
possible
to
to closer and closer
closer to
to Q
Q
star of
actually.
A. Correct.
Hmm.
But note that I never have access to Q star of A. In the RL problem, Q star of A is something that we never have access to. Whatever we have is some sort of an approximation that we reach at.
So the assumption is more of what if you do this more, you'll be closer and closer to Q
Correct,
star.
correct, correct.
Hmm.
More number of sampling that you do, the more closer you are to the original
Hmm.
Q value. Okay.
Hmm.
And the first optimality says that if you keep on doing it asymptotically you will eventually reach the correct solution.
Correct. Correct.
Yeah. So that's what this asymptotic correctness means.
Okay. Thank you.
Okay. Cool. Now another advantage that UCB algorithm gives is that the bound it gives on the regret optimality, it's superior than the bounds that one would typically get by using a softmax or an epsilon greedy algorithm. So maybe we talk about the concentration bounds. So if you have looked at the week 2 lecture, so far. So you would find that there has been a lot of proofs that were done that like proves the correctness or the rigidity or the uh, boundedness of the UCB1 algorithm. They take a look at the regret bound, then the pack bounds, and so on. So, do you want me to go through the proofs, or I just give a top overview of that?
You can give a top overview, sir. Yeah, I don't know the other participants, but top overview.
Okay. So I can go through the proof, but I feel Professor has explained it nicely in the lecture. Maybe a viewing of that would help you. But what I feel is that proof is more of a theoretical analysis. Okay, practically, you are uh, not going to use that when you are trying to solve an RL. It just gives a theoretical bound on how good a particular algorithm is over the other algorithms that we have. So that's why we have three measures of comparison. One is the regret optimality, one is the pack optimality, and first one is the asymptotic correctness. Okay. So here the theorem says that for my UCB1 algorithm, so for all k greater than 1, where k is the total number of arms, if UCB1 algo is run on k arms having arbitrary reward distributions between uh, 0 and 1. Okay, so my reward distribution, I scale it between 0 and 1. If this is the case, then my expected reward after n pulls is at most. So this quantity is 8 sigma I star I conditioned on q star a star ln n by delta I plus 1 by omega pi squared by 3 times this is delta j, where my delta I is basically q star a star minus q star I. Okay, so here I'll just quickly explain what I've written. So if I have k arms, my UCB algorithm gives me an upper bound. My regret can not be more than this quantity. This is the upper bound of the regret that I'll get if I implement the UCB1 algorithm. I can get smaller regrets, but my regret will most definitely not be greater than this quantity. Okay, so this is an upper bound over that. So what it tells me is that this is 8 sigma of my q star I is less than q star a star. So why I have taken this quantity is because there is a delta I in the denominator. My delta I is basically q star a star minus q star of I. So that's why taking I'm only taking the non-optimal arms over here. Okay, because if I take the optimal arm, this quantity becomes 0. And here I don't do that because if I have a 0 in the numerator, then it's fine, right?
So, in some sense, um, this tells you how far your queues are away from your queue optimal, is it? In the sense, you have four of these arms: Q1, Q2, Q3, Q4.
Mhm.
In the regret thing, which one are we selecting? It's a random thing, right? There's no
No.
specific.
So what happens in regret is, let's say, let's say my original, I should maybe use some. So let's say this is my original Q value or the true value. This is my Q star of 1. This is my Q star of 2.
Yes.
This is my Q star of 3. And maybe this is Q star of 4. Okay.
Yes.
Now, if I know the original value from the beginning, I know my arm 4 is the best arm. I
Correct.
do that infinite times. I only pull
Yes.
arm 4. I don't look at anything else. Okay.
Yes.
But because we don't know that, initially you pull each arm once, you get some bound, then you end up pulling arm 1 sometimes, you pull arm 2 a few times, then you pull
Yes.
arm 3 few times. So there is some delay that is happening, right? When you reach arm 4.
Yes.
Before you figure out what is arm 4, you're doing some trial and error, some exploration, but
Correct.
eventually you're reaching arm 4. Okay. So the
Yes.
time that you have lost, okay. So this is known as a
Hmm.
regret.
So this tells me the number of times I have to pull randomly before I come to realize that Q4 is the best arm.
Not that quantity. It tells me that, let's say, this quantity is, let's say this is the uh, my Q star A, and I would have
Hmm.
gotten the maximum reward if I had pulled arm A star from the beginning. But because of
Hmm.
this, I am doing some exploration. So this
Correct.
area that have colored in yellow is known as the regret area.
Okay.
So
Okay.
my goal is to basically, like,
Minimize this.
yeah. So the strength of an algorithm depends on how small is the regret area, how well I'm able to optimize my regret.
Hmm.
So what this equation tells me is that my regret can be large, but it cannot be larger than this quantity over here. So this
Okay.
is a theoretical bound on the regret that we have for UCB1 algorithm.
But shouldn't it be also having some parameter suggesting that you have to at least minimum do so many pulls before this comes into
No,
play?
it
Or
might happen you are lucky. So you have pulled the first arm, you got something, and
okay, okay, okay,
you might hit the jackpot on the first try. Okay, so
okay.
you don't have any minimum bound on that, on this kind of thing. Okay,
Oh, thanks a lot.
sure. Uh, so since we are not looking at the proof, maybe what I can do is, Mhm. Yeah. So I'll quickly discuss the. Okay, so I don't know if this will be useful because uh, if we are not looking at the proof right now, but for proving that thing, so we make use of a known mathematical bound known as the Chernoff-Hoeffding bound. So what it tells me is that let uh, my x1 dot xn be random variables with common range 0 to 1, such that my expected value of xt given x1 dot xt minus 1. So given all the previous random variables that I have sampled so far, is basically mu. What it tells me is that there are n different distributions. All of them have reward between 0 and 1, and all of them have the same mean. Okay, the uh, standard deviation may vary. All of them have the same mean. So in this case, we define a quantity. Let my S of n is x1, x2, dot dot dot, x of n divided by this thing. So if you look at the bandit problem, this is similar to my capital Q, right? My Sn is similar to my capital Qt, my reward estimate, because my x is the reward that I'm sampling and I'm averaging that. So that's my capital Q. And xi is the number of time each is the different time arm I is pulled, okay, at time n. And looking at this, what we say is that the probability Sn is greater than mu plus epsilon less than e to the power minus 2 mu square n, and the probability that the opposite holds true is e to the power minus 2 sigma square n. Okay. And this is true for all values of epsilon greater than or equal to 0. Now, what it tells me is, now you know Sn is now, you can think Sn to be related to my Q of j. You can see the similarity, right?
Yes.
And my mu is nothing but my Q star j, the true value that I want to reach.
Yes.
Okay. Now what this quantity tells me, okay, this is a theorem in itself. Okay, what I'm writing is separate. So what this quantity tells me is that, let's say this is my mu value. Okay,
Mm-hmm.
this is my mu value, and this is my Sn value.
Mm-hmm.
So the distance between that should be at max epsilon. So if the distance between this two quantity is epsilon, I can say
Mm-hmm.
that the arm that I've selected is epsilon optimal.
Mm-hmm.
Okay, maybe I should forget mu and Sn. I look at it from a bandit perspective. So let's say this is Q star A, and this is Q star A, and this is Q of A. Okay, so if the
Mm-hmm.
distance between them is epsilon, I say that my arm A is epsilon optimal.
Mm-hmm.
Now, what this tells me is that, what if the estimate that I have made is greater than mu plus epsilon, is greater than my Q star plus epsilon. That means the estimate that I have made is more of a gross overestimation than the true value.
Mm-hmm.
So this basically tells me the probability of making a gross overestimation. So this is bounded by e to the power minus 2 epsilon square n. And this is true for all epsilon.
So you don't know Q star A here, right?
I don't know that.
So this is
This is for the
what was
theorem
telling
proof.
us that what was telling us is that, so how do you do the maths? How do you compare the two entities if one is not available?
We don't come. This is available as in this is not available during the execution part. Here we are looking it from a research point of view. Okay, we are trying to analyze how close it is to the
Okay.
true solution. So when I'm actually doing the arm pulling, I don't have access to Q star A. All this
Correct.
regret optimality, pack optimality, that is done to test the robustness of an algorithm. That is done later part. This is for the
Post that. Okay.
so this is for the evaluation part. Okay. So in the evaluation, you might have Q star A. Okay. So you have all this quantity. I'm just trying to put an upper bound on that. Okay, how close I am to the known solution.
Does this also give you any kind of impression as to how many samplings you have to do before you reach that optimal level? Is that something one can interpret from here?
That is from the pack optimality. So pack
Okay,
optimality, my regret optimality deals with the rate of convergence, how fast I can converge
Hmm.
to the optimal arm. My pack optimality gives me, so given epsilon delta, how many number of arms I pull
That's
before
pack.
I reach that pack optimality.
Hmm.
So pack stands for probably approximately correct.
Hmm.
So it is this equation.
Hmm.
So the probability that my q star of A is less than equal to q star A star minus epsilon. Again, the same thing. If I bring
Hmm.
the epsilon to this side, I have q star of A plus epsilon should be greater than q star A star. That means the difference between them is epsilon.
Hmm.
See that?
So you're saying this particular algorithm is used post learning, trying to understand
Mhm. Yeah, the
when to,
optimalities.
trying to understand how close are you to
Correct.
the
How
optimal
how
solution.
good my algorithm is, how close I am to the optimal solution.
Hmm.
This is not available to us in the learning phase.
This is not available to the learning
No,
phase.
no. When I'm learning, I just do sampling. I get the capital Q value. I do my stochastic averaging. Then I do this orange. I pick the
Hmm.
next term based on the orange equation. And
Hmm.
eventually I expect I reach the correct term after
Hmm.
some number of trials. Okay.
Hmm.
This is a comparison. Ki how good I can be, or what is the minimum number of arm pulls I need to do, or what is the minimum regret that I have before I reach
Hmm.
that quantity. Okay.
Hmm.
So this quantity is for a gross overestimation, the first term here. And the second
Mhm.
term is for a gross underestimation. That means if the estimate of the arm that I made is less than mu minus epsilon, so the distance between them is more than epsilon or
Hmm.
on the upper side and the lower side, then the mistake, I mean, the probability of making that error is bounded by this quantity over here. So you can think of it as the probability of making error of over or underestimation. Sorry. Okay. The screen is visible again, right? Yeah, so this is basically a bound on the probability of me making a mistake in over or underestimating some quantity. Again, if you look at the proof carefully, if you go back to the video, you can see that when I'm trying to prove this a quantity in pink that I've highlighted, we actually make use of that concept to figure out key. Okay, this proof is there. Okay, so this was just an intro to my the Chernoff-Hoeffding bound. So the proof is actually very large. It's a like 3-4 page proof. So it's better I skip it for now. Yeah. Second is something known as a pack bound. Okay. So when we are looking at pack bound, so let's say I define some naive sampling algorithm. So I say this is a naive epsilon delta algorithm. Color it. So here my input is some quantity epsilon, some quantity delta, and my output is basically an arm. Okay. So what you're doing is for each arm in the total action space, do. So I sample arm A L number of times. Okay. So here my L is equal to 2 by epsilon square ln of 2k by delta, where k is the number of arms that we have. Now, after I've done that, let Q of A be average reward of arm A. And then I end the for loop, and then my output is basically A prime is equal to argmax of QA. Okay, so what my naive epsilon delta algorithm tells me is that I I give some input quantity epsilon, some input quantity delta, which are some positive numbers, and the output I expect is the optimal arm. So for each possible actions in the action space, I pull each arm L number of times. So here L is basically this magic number over here. If I pull the arm this many number of times and then compute the Q value, which is the average reward for arm A, and after that, whatever output that I get, which is argmax of my arm A prime is epsilon optimal. So this is the claim. You see, if each arm is pulled L number of times, where L is this magical quantity, and after that I just do argmax of Q of A. So the arm that I get will be epsilon optimal, which this is the claim of this algorithm. And one theorem is there which states that my naive epsilon delta is an epsilon delta PAC algorithm, PAC algorithm with sample complexity of K by delta. Okay. So far, so good. Now, how do
Yeah.
we get this magical number is a proof in itself that there is another proof on why this is an epsilon PAC algorithm. But if you look at the proof from the lecture series, you will see that at most each arm needs to be pulled by this much quantity. And if I do that, I am within epsilon distance of my optimal arm. This is the claim. Okay. Now the question is, can we do better than this? So my sample complexity is basically there is O of K and there is log K. So if I look at it, just this is more or less O log N, right? Because my epsilon and delta are constants. The question is, can we do better than this? Can we look at some other algorithm that gives me with less number of arm pulls? Okay, so for that, we discuss the median elimination algorithm. Okay. So here the algorithm is slightly different. Oh, let me just get my charger. Please hold on. Okay, sorry, we are back. Yeah, so we are looking at the median elimination algorithm. The way this is different is, you can hear me, right?
Yeah, we can hear you, sir.
Okay, thank you. So my input is again some quantity epsilon, some quantity delta, and my output is again an arm, right? So the way this works is we say let S1 is equal to A, where A is the total action space. Then my epsilon L is basically epsilon by 2, and my delta L is basically delta by 2, and my L is 1 in the beginning. Then I repeat. So what I do is I sample every arm A belonging to the space SL. So I actually sample this arm for this many time. So it's epsilon L the whole square by 2 times log of 3 by delta L. Okay. And let QL of A denote its value. Okay, now find the median of QL of A, which we denote by ML. Now SL of 1 is SL minus L, all the arms are less than ML. Okay, now look carefully. What this algorithm is doing is, so I start with S1, which is the entire action space, which is the entire arm. So if I have a 10 arm bandit problem, so I have 10 different arms that I have to pull. So initially I pull all the arms this number of times. Then basically I compute its Q value for the arm after pulling each arm this many number of times. Now after doing that, I arrange it from in an ascending order. So I arrange it based on its Q value. So the arm which has the highest Q value is has the highest priority and so on. And I define the median, okay, of that quantity. And after that, what I do is I eliminate all the
all the
quantities
quantities
that
that
are below
that
the
are below the
median.
median.
Okay, I think
Okay, I
there's some
think there's some
echo.
echo.
Okay, so I remove all the quantities which lie below the median, and after that I update my epsilon L, delta L, and increase the L, and I keep on doing that until I am only left with one optimal arm. So you see the way this is different is in the naive algorithm. What we are doing is we pull all the arms for some L number of times. Based on that, we decide, okay, this arm is correct, and we can guarantee that the arm that I pull from this is optimal, is epsilon optimal arm. But for that, I need to have a sample complexity of O n log n. That means uh, to find the optimal number of arms, I have to pull around n log n. I need to make n log n pulls to reach the optimal arm. So an improvement over that is instead of doing that way, we introduce a round based system. So there are, let's say, L number of rounds. Okay. So imagine, okay, I'll again bring up the restaurant example. So let's say you have again moved to a new city. You have 10 different restaurants to try from, and you have to figure out which one is your favorite restaurant, right? What do? You go to each restaurant some number of times, which is this magical number that I've tick marked. So you go to all these restaurants this many number of times. You note down how satisfied you are while eating the food. That's the Q value for that restaurant. Then you make a list, okay, in an ascending or a descending order. Okay, I arrange them based on their Q values, and then I figure out the median, and I delete all those restaurants which lie below the median quantity. That means half of the restaurants are gone. For the next round, I'm only left with 5 restaurants. I repeat the process again. I again go to those 5 restaurants for this magical, uh, this many number of times, which is again this magical quantity that we have. Again, I figure out what is the Q value that I have on eating over there. Then I remove half the restaurants which lie below the median, and I keep on doing it until and unless I am left with only one restaurant. So this is the difference between the naive algorithm and the median elimination algorithm. Eventually, what we are doing is the same thing. There, you pulled each arm some certain number of times, and now here you're doing some round-based pulling. But the main difference here is uh, this quantity that you have, the magic quantity over here, the number of arm pulls that are required in the median elimination algorithm is actually smaller than the number of arm pulls that is needed in the naive algorithm. So the theorem again I can mention. So here the theorem states that the MEA epsilon delta algorithm. So this is the MEA epsilon delta algorithm. This is the median algorithm, median elimination algorithm with parameters epsilon delta. So again, this is epsilon delta pack with sample complexity k by epsilon square log of 1 by d, 1 by delta. Okay, now if you look closely, the term inside the log quantity is a constant, right? Only this quantity is here, which increases. So the sample complexity increases when I increase the number of arms. My epsilon and my delta are constant quantities. So if I look at it, so this is nothing but an algorithm that gives me O n sample complexity. So from n log n, I made it to a sample complexity of n because of this difference that we are looking at. So this is like a round-based elimination system. You sample each arm some number of times, arrange it according to the ascending order, delete half the element, repeat, and so on until you reach the optimal arm. Okay. Now again, you might say that, okay, if I have sampled this arms so many number of times, there might be a chance, right? There might be a chance that uh, the actual good, the optimal arm that is there, it gets eliminated in some previous round, right? There might be a possibility because the estimate might be incorrect or something. Maybe I needed to uh, put more number of estimate and so on before coming to a conclusion. So that argument always comes up. But again, this algorithm claims that the probability of making that error is at most delta. Delta is the probability of making an error. So here delta is actually an input to the algorithm. So this delta tells me, my epsilon tells me how close I want to be to the true solution, and delta tells me with what error I want to be close to the correct solution. So if delta is very, very small, if you put delta to be very, very small, so this number changes and it gives a theoretical guarantee that if I use this method, I will always get the epsilon optimal arm. Okay. Yeah, maybe I should also color this. Okay, so this was the difference between the median elimination algorithm and the naive algorithm. Again, the proof is there in the lecture as to why, how we exactly get this guarantee and so on. I don't want to go into the proofs right now because I actually have some coding related activity which I plan to do in like a couple of minutes later. I just need to finish this last part, and then maybe we'll look at some coding related issue, because what I feel is the course that we are doing right now, the course on reinforcement learning, is more or less theory. Okay, but in real life scenarios, you might come across in your job or in your internship or any other application based, you need to know the implementation part of reinforcement learning. So I feel that in this live discussion session, maybe I can start giving you small implementation problems, maybe give you some 10-15 minutes to figure out, and we can discuss the solutions. It will be interesting for you and something different from what you have been looking at the lectures so far. Okay, so I just finished this last part, which is the Thompson sampling. Some people also call it as the posterior sampling. Okay. Okay. So far, whatever we have been looking at, wherein we are trying to estimate the true Q value of the arms, we are assuming that there is an unknown underlying Q star quantity behind each arm, and we are trying to reach that by making some samples of each arm. Okay. But another way to look at it is that what if we try to estimate the original Q star value based on some other algorithm? So the way you look at it is, in all the sampling methods that we have looked at so far, we do not make any assumption about the original Q star value. So Q star has no a priori assumption or knowledge. So this is given as is, and we are trying to estimate get closer and closer to the true estimate, the true value of for each arm. Okay, maybe this is for arm A. Now, how Thompson sampling differs from that perspective is that we assume that my true value, Q star of A is say sampled from some distribution. Okay, so let's say this is my probability axis and this is my reward axis. Okay, well, let's say this is the distribution of, let me first draw. Okay, so let's say this is the distribution for Q star of 1. This is distribution for Q star of 2. This is distribution of Q star of 3. And this is distribution of Q star of 4. We are making an assumption here. Okay, so this something is some random assumption we start with. Ki my Q star of 1 is from this distribution. Q star of 2 is from this distribution. My Q star of 3 is from this distribution and so on. Okay, now once we make this assumption, what we do is we draw sample from each arm. We draw one sample from each arm. So here in this case, I'm sampling from a Gaussian distribution that I've drawn over here. So let's say this is the arm that I sample. Okay, I should. Yeah. This is reward. So let's say I draw a sample. So this is the sample I get when I sample from Q star. This is the value I get. This is the reward I get. This is the reward maybe for sampling from this thing. And let's say this is the reward I get from this quantity. Okay, this is the 4 sample that I got based on the underlying assumption that this is from this distribution. Now what I do is I actually look at the true mean value. How do you look at the true mean value? Because I know the distribution, right? So I can get the corresponding mean. So if I look at their mean value, and now I want to see ki, from this mean value, based on this mean value, is there any difference? Like in the ordering part. Okay, so here my blue is greater than green, which is greater than red, which is greater than orange. Okay, but if I look at it from the mean perspective, then my green is greater than blue, then red, then orange. Okay, so there is some discrepancy which is happening over here. So that's why this tells me that I need to update the belief that my blue shouldn't look like this, but rather something like this. I maybe decrease the probability here so that that issue doesn't come up again. So I keep on doing that repeatedly until I get a very smaller standard deviation, so that whatever estimate that I have is closer to the original Q star value. Okay, so this is the basic idea behind Thompson sampling. So the reason, so this is a kind of posterior sampling because we usually don't assume any a priori information about the Q star value. But here we are actually starting with some assumption of the Q star value. And based on the samples that we have drawn, we are making improvement over that. Okay. So this was all that was covered in week
So,
2.
but what is the advantage of doing this? In the sense, if you have to choose n-
A
between maybe
priori
using
sampling. Yeah. So
you,
advantage wise, you can't say that one method is advantageous over the other, but there might be some use cases where this approach might work as well. So this is another
hmm,
approach of looking at the problem.
hmm.
So
Because
relatively,
here, so you're saying here we assume there is some distribution there. The other way, prior to this, we were not assuming anything.
no, no.
Hmm. Okay, sir.
Yeah. Uh, yeah. So I've covered what I was there in week 2. If you want me to go back on something, please feel free to ask me.
Sir, if you don't mind, I have this
Yeah.
question. Not just, of course,
Hmm.
the professor has given some instructions on week 3 also.
Okay.
I am not able to understand overall how does all of this come into play. In the sense, uh, you are looking to what you've explained in now are the different ways to identify the
To
best,
solve the bandit problem.
the
Bandit
bandit
problem.
problem. But where
So
does it plug into RL? In the sense, all these are ways to find out the. But where does RL and bandit problem come together? In the sense that I have not understood. So.
So bandit is actually not an RL problem if you look at it. It's a simplified RL problem. Okay. After the bandit, we actually go to the full RL problem. So what happens in RL is uh, what happens in RL is so there is an agent. So there is one agent. Okay. There is a particular environment. It's usually the real world that we have. Okay. So this agent could be you. Okay. So what you're doing is you're taking some action in the environment, right? And the after you take an action, the environment actually changes or whatever state you have changes. So let's say here the state is whatever I see in front of me. So let's say I see the Google Meet screen in front of me. That's my state space. So if I take an action, which is if I close my eyes, then it's all black, right? So that's my new state. So based on that, I reinform my decision. I take another action. So my environment basically gives me the observation, and then I evaluate it with some reward. Okay, so the environment also evaluates the goodness of an action. So the action that I've taken, whether to reward it highly or to penalize it. Okay, now if you look at the bandit problem, you see that the bandits don't return any observation. So there is no notion of an observation in a bandit problem, right?
In observation, you mean to say?
You don't
Sorry, I don't.
maintain any prior history. It's like you take an action, you get a reward. That's it. The
That's it. Correct. So
next
I think
you pull is independent.
so the professor was saying, is it correct to say there's no state? I'm not sure if the
Correct,
answer
correct.
is correct.
Yeah, yeah, yeah.
Hmm?
There is no state. There is no notion of a state space in the bandit
Hmm.
problem. So this is
Hmm.
an independent identical distribution. It's similar to a coin toss. If I toss a coin one time, the second coin toss contains no memory of the previous coin toss.
Okay, independent completely.
All my decisions are independent. I
Hmm.
don't say, ki, okay, last arm pull, I got this. So based on that, I do this. I mean, you do that, but that's included in part of the reward. There is no state that is informing your decision.
Hmm.
Okay. So
Hmm.
in week 3, week 4, we move from the bandit to the full RL problem. So
Correct.
this, so the RL that what we are doing at with the bandit problem, it's not an RL problem.
Okay. Okay.
So this comes under the area of immediate RL. It's like
So, sir, so there is this concept, right? If you do week 3, which you must have also, there is this
mhm.
concept of reward which comes through accumulated reward. What? Yeah. So what you're saying is this is instantaneous. You do something, you forget about it, you just
Correct,
do the
correct,
next thing. There is
correct,
nothing. There's no concept of
correct,
accumulated reward. Just a reward. That's it. You do it and finish it.
correct.
Okay, sir. Okay.
There is no, so you do a reward, you finish it. So let's say full RL problem would be like if I want to go from place A to place B. Okay. So I start from point A, I want to go to point B. What could be my state? My state could be the distance from point A to point B, right?
Hmm.
So let's say
Hmm.
I want to go from Bangalore to Delhi. Okay.
Yes, sir.
So if I go south, I'll get a negative reward because the distance increases.
Yes.
If I go north, I get appropriately rewarded. So my
Yes.
each step has some associated memory, so it tells me to go in the correct direction or not. So it's a
Hmm.
sequence of state action pair that I need to make before I reach my final state.
Hmm. Hmm. Okay.
Okay, so my state is
If
actually
you
informing my decision.
don't mind, give me an example for immediate RL if you don't mind, just for my understanding.
Immediate RL.
No, whatever you said, this is immediate RL, right?
No. This is a full RL problem. No navigation.
No. Bandit. Uh, the bandit problem is only for forget, right? You take the reward and you forget, right, sir?
Correct. Correct.
Can you give me an example where you'd want to use this kind of a concept, sir?
Uh,
Like the Bangalore to Delhi example. That makes sense to
th-
me for an RL, which is a full RL.
correct.
That I've
Oh,
understood.
you want another problem wherein uh,
I would
you
use
want to see
this. I will use Bandit.
immediate.
Is there something like that we can talk?
There are few examples, but if you want a real life example, I can't think of any
Okay.
because
Okay.
this is more of a
No.
toy problem.
Okay, sir.
Just to
This
get
is it's
started
just
with
to yes.
yeah,
Okay, sir.
yeah.
Thank you. Thank you so
It's like a
much.
toy example, but eventually we move to full RL. But before moving to full RL, it's important to know what all is happening so far.
Sure.
Okay, so
Thank you, sir.
okay. Now what I'll do is okay. Can you see my screen?
No.
Not yet. Now?
I can't see, sir.
Just a second. Okay, I'll share again. Now?
Sorry, I can't see, sir.
Okay.
It said
So
now I can see, sir. Yeah.
okay,
Now I can see.
fine.
Mm,
You can see this Jupyter notebook.
I can see, sir.
Okay. So what we'll do now is we'll look at a small tutorial to understand this multi-arm bandit problem.
Mm,
So I have written some code. I have also left some blanks, so it's for you to fill. So it's 7:45. Take 10 minutes. We'll discuss solution in the last 5 minutes, or maybe next class, whatever is fine. So maybe we discuss it next class. You take it as a
okay.
take-home assignment. So I hope all of you are familiar with Python and use of Jupyter notebooks or Google Colab, right?
I'm sorry, I'm not, sir. Uh, I don't have that background.
Okay. That's fine. So okay, I'll just mute you. So all I'm doing is here, I'm importing all the necessary functions, which is for plotting, for seaborn, for pandas, and display part. So here I have a simple description of the multi-arm bandit problem. So at each time instance, you are repeatedly faced with choice among three different options. After each choice, you receive a numerical reward, which is chosen from a stationary distribution, and it depends on the action that is selected. So the objective that we have is to use epsilon greedy and softmax algorithm to asymptotically estimate the arm with the best expected reward while we balance exploration and exploitation. So for visualization purposes, what I'll do is
Can you please fix the echo once?
Which one?
There's an echo.
Oh, I think. Okay. I think somebody had unmuted. So that's why. Now it's fine, right?
Yeah, it's fine now.
Okay. So what we are doing is I'm taking four distributions. One is the Gaussian distribution. One is the uniform distribution. There is a Poisson distribution and the beta distributions. So I'm selecting the parameters randomly. So for the Gaussian distribution, what I have is mu and sigma, right? For uniform distribution, I have the upper bound and the lower bound. For Poisson distribution, there is a lambda parameter, and for the beta distribution, there is again a lambda parameter. Okay. So all the parameters values I am selecting randomly. Okay. So I select two random mu and sigma. I select two random low and high, two random lambda value, and two random AB values. And based on that, I calculate the true means. Okay. So for a Gaussian distribution, the true mean is basically the mu value. For my uniform distribution, it's high plus low divided by 2. For Poisson, it's the lambda value. And for beta distribution is A by A plus B. So this is the true value, true means. What this true means tells me is that this is the Q star, right? This is the true mean value. I run this. So here the above numbers are chosen randomly. There is no particular significance. For real world problems, true means will not be available to you. Here, since we know the parameters and the distributions, we can analytically calculate. So this is just for the sake of exercise. So this is a function which is pull MAB. So whatever arm I give, so arm here is none. So whatever arm I give, which is either arm 1, arm 2, or arm 3, it will return me the appropriate reward. So if arm is 0, 1, because I have 8 different distributions. So this is 0, 1, this is 2, 3, 4, 5, 6, 7. Okay, so that's how the indexing is done. So if arm is 0, 1, then I sample a reward based on the mu and the sigma. If the arm is 2, 3, I sample from a uniform distribution with the parameters low and high. If arm is from a Poisson distribution, I sample from Poisson with the lambda parameter. And if it's from a beta distribution, I sample from beta distribution with parameters A and B. This is something that we have selected arbitrarily. Now what we are doing is let us pull each arm 1000 times to get enough samples for estimation and plotting. Okay. So what I'm doing is all the rewards initially I'm setting to be 0. For each arm, I am pulling each arm 1000 times. I'm calculating the reward and I'm storing it. Okay. Okay, so far so good. Now that we have collected samples for each arm, we can analyze them. So I'm just analyzing the estimated value with the true value. So this is the true mean. This is the estimated mean. What I've done is I have pulled each arm 1000 number of times, and this is the tabular distribution of the true mean and the estimated mean. Now, if I actually plot it, so this is the plotting part. So if I run this, so this is how the distribution looks. Okay. So for arm 0 and arm 1, so this is a Gaussian distribution. I sampled 1000 points. I get this curve. This is the green line is the true mean. Red line is the estimated mean. And similarly, this is for the uniform distribution. We go below this, we get for the beta distribution, then for the, sorry, it's a Poisson distribution. This is the beta distribution and so on, right? So the above plots show examples of 4 common types of distributions: Gaussian, uniform, Poisson, and beta, with 2 arms for each. So it can be incredibly useful to know the underlying distribution, but in real world problems, it is extremely difficult to find out, right? If we know the true mean, it's good, but in real world, it's extremely difficult. See here, we had to pull each arm 1000 number of times. So for 8 arms, I pulled 1000 into 8. So I did 8000 number of trials to get close to the optimal arm. Okay. But that doesn't stop us from estimating their properties such as mean or variance, because estimating is what you do when you don't know and you know nothing. Okay. So Now we implement the epsilon greedy and the softmax on the Gaussian bandits. So this was just for an experiment part. It's like if each arm is pulled sufficiently enough, you eventually reach closer to the true mean, right? Now, what I'll do is we are actually trying to implement the epsilon greedy and the softmax. So the goal here is I want to minimize this number of arm pulls, right? That's the whole goal. I don't want to waste pulling each arm 1000 number of times. What if I get to the optimal arm in like 50 or 100 arm pulls or so? So that's where RL comes in. We want to figure out which is the optimal arm with small number of arm pulls. Okay. So here we implement the epsilon greedy and the softmax on the Gaussian bandits. The bandits are Gaussian now. Okay. All the reward distributions for the bandit are assumed to follow a Gaussian distribution. So again, I import all the functions. I select number of arms to be 5. So my number of arms is capital K, right? When I look at the K arm bandit problem, my K is equal to 5.
Sir, for all these algorithms, is it
Yeah.
expected that all the arms have the same distribution, or they can have,
No,
just
no,
like
no.
the other example that you showed, it
They
can have
can have
different distribution?
different distributions.
Okay, okay. So there's
They can
no
have
specific requirement.
no, no, no. For for this exercise, we are assuming it's a Gaussian arm, but this need not be true.
This might not be true. Okay.
Yeah, because by doing multiple number of samplings, you eventually try to converge to the original mean. Okay.
As you just showed earlier,
Yeah, yeah, yeah.
all the five had different distributions, and by sampling a large number of them, we actually reached the right numbers.
Correct, correct. Now this is a function for pull MAB. So the reward I get is something which is sampled from the normal distribution, and the mu's and the so here I have fixed the standard deviation to be 1. So all the 5 arms have the same standard distribution. Only the mu's are different. And based on which arm I select, I'll sample from that particular distribution. Okay. Now the task for you is, so this is the function to implement the epsilon greedy algorithm. So what I do is, this Q is the NP zeros number of arms. So this is the capital Q estimates, is the empirical expected reward. We initialize it to 0, all the arms. Capital Q is 0. Time sampled, what it does is it keeps track of the number of times each arm has been sampled. So you keep a track. So if you sample arm 1, you update that. You do +1. So arm 1 +1. I have sampled it 1 time. If you sample it twice, +2, and so on. Then list of 5 lists to show the sequence of the estimate of Q estimates for each arm over time will be useful to plot the convergence of Q estimate. So this thing is basically the Q of all arms over time. So what I'm doing is, so this is a list of list. Okay. So I'm basically storing the Q values of all the 5 arms that I have. Then this is a list to store all the rewards that are obtained. This is the regrets list. Now here is where you start coding. Okay. So for t in range 2000, for 2000 iterations, I first pick an action epsilon greedily. Okay. So you write a code how that epsilon greedy action is picked. Then you increment the sample count, which is the sample count, this quantity. You increment for that particular arm. You don't do +1 for all. So if arm 1 is pulled, though you increment arm 1. Then after that, you pull the arm to get a sample reward using the pull MAB function. So you have a function called pull underscore MAB. So if you put that arm, you get a reward. So it's if you put arm 1, you get corresponding reward. So you implement that. And whatever reward you get, you store it in the list for later plotting. So you store this in the rewards function. And then you do the stochastic averaging. You know stochastic averaging, right? Something that we saw in the first slide itself. That new estimate is old estimate plus step size target minus old estimate. This QT is equal to QT minus 1 plus 1 by N by A, RT minus Q. The first slide of this lecture that I have. If you have forgotten, I'll post the slides. You can get the equation. Now storing each Q estimate at the current time step in the corresponding list within Q of all arms over time. So you store the Q value and then comment out the pass when code is written. Okay. So when after the code is written, you comment this pass. Okay. Comment means you just put a hashtag on front of it after you have completed the code. Otherwise, it will throw an error because I have started a for loop without writing anything. Okay. And then what you get is the Q value, the rewards, and the Q of all arms over time t. If you run this, you get some value. Now you won't get anything because it's empty, right? Now I generate some random mews. So I generate a set of means for the Gaussian bandit arms using the standard normal distribution. So that means for 5 arms that I have, I'll generate 5 random mews. My sigma is fixed to be 1. For each arm, the standard deviation is 1. Now I'm trying to run the epsilon greedy algorithm for 3 different values of epsilon. So my number of arms is num arms, which is 5. My mews is this mu. And my epsilon greedy, so which is my epsilon greedy part? This is epsilon greedy. So what it takes input, the epsilon value, number of arms, mews. So here we are actually trying it for 3 different epsilon values. So this is for epsilon 0, then for epsilon 0.01, which is 1% exploration. This is for epsilon 0.1 for 10% exploration. You might try it for epsilon 20, 30, 40. You can play around with it. And then after that, you plot the convergence of Q estimates over time. So if I run this first, I run this. And now this is a plotting function. If you run this, you should get a neat curve over of all the arms. Okay. So this dashed lines, this is my Q star value. This is the true value, or this is the mu value, right? So you want to see the graph, it should increase and saturate over this line. So my yellow solid line should converge to this line. My blue solid line should converge to the blue dashed line and so on. So this is what you will see for plot. This is for epsilon 0. Okay. This is a plotting function for epsilon equal to 0 here. Now, similarly, you plot something for epsilon 0.1 and then plot something for epsilon 0.1. Okay. So I think you can start with the epsilon greedy algorithm. The plotting function is given. You make appropriate changes. Just change the epsilon value. You will get the answer. And this is the major part where you need to do changes to figure out how exactly you do the epsilon greedy part. So if you do this, you will get clarity of how epsilon greedy works and your understanding will improve. So maybe try this. So it's a take home assignment for you guys. I will share the link in the chat. And also when I upload it to the YouTube, I'll put the link in the description there over as well. So you can see that. So you open it. So right now, you only have viewing access. Okay. You can't do any editing because if you do any editing, it will show up here. So first thing you do, you open it, you go, you make a copy. So whatever changes you do, it is the changes you make is in your own copy. Otherwise, if I give editor access, everybody makes changes and it messes up others' code. Okay, so if you want to work independently, make a copy of it and start making changes over here. I think, yeah, that's it that I had for today. I think in week 3 beginning, we can discuss the solution and see the plots, how it looks. If you guys can come up with the solution, it's great. Otherwise, I'll discuss the solution. So yeah, that's it from my end. If you have any other questions, please feel free to ask.
Thank you, sir. Thank you.
Okay, fine. So no more questions, right?
Yes, sir. Thank you so
Okay,
much.
sure. No issues. Okay, thank you. Have a nice weekend. Good night. I'll stop
Bye.
the
Good
recording.
night.
Good night. Bye.
Thank you.